true.
So friends, what today we want to discuss is what are the field automorphisms are. So the question is, what are the field automorphisms of R is the real numbers, right? So friend, to deal this problem, we will learn what is the homomorphism of groups, what is the homomorphism of rings, and what is automorphism of field. Homomorphisms, we will learn homomorphisms. Next we will learn that, and the next point we will learn that any automorphism of R fixes Q. Means if sigma is an automorphism from R to R, then sigma Q will be sigma R will be R for all R belongs to Q, right? So, and another point we will learn is that in course of the proof, we'll use the fact that the monotone increasing a monotone increasing sequence which is bounded above converges to its supremum, right? Similarly, a monotone increasing sequence, a monotone decreasing sequence which is bounded below will converge to its LUB, this tower bond. Not so this tower bond. This tower bond is same, so it is GLB, greatest lower bound. Sorry, this is infimum or infimum, or it is this tower bond, LUB, right? Another thing we'll learn in the course of the proof is that if sigma is an automorphism from R to R, then sigma respects inequalities. So, this one respects inequalities means if A less than B and A and B in R, then sigma A it is an automorphism, then sigma A less than sigma B, and finally we will prove that sigma is the identity. Here is our overview of the proof, right? So friend, let's recall what is a homomorphism, what is a field automorphism. So to understand a field automorphism, we have to know what is a group homomorphism. What is a group homomorphism, and what is a group homomorphism? So for let's say R is a field. So what is a field? Field has two binary operations in it, is plus and multiplication, right? With this to plus, it is an abelian group. So abelian group, and with this to dot multiplication is also an abelian group, right? The two operations, but it will be abelian group. Okay. So what field automorphism means is, R, if sigma is a field automorphism from R plus dot to R plus dot, means a field automorphism. If sigma maps R plus to R plus a group homomorphism, right? A group homomorphism. Next, what we'll need? We have sigma maps R. Is a plus, we have group homomorphism. With the multiplication, we will have another group homomorphism. Same map, but two homomorphisms. A group homomorphism, right? Group homomorphism. And the other thing which you regard for automorphism, automorphism means a bijection, right? So it is the isomorphism, or it's homomorphism, and bijection means it's isomorphism. Isomorphism means it's automorphism. Iso means automorphism, right? So r plus dot to r plus dot is a field on automorphism. So it is have these properties, right? So friends, let's look what do you have. R plus. So let's recall what do you study in group homomorphism. Suppose S naught is a group and T star is a group, and say maps a phi. Phi is a group homomorphism. Right? So what does it mean? It means phi of A compose B. A is an element of S, B is an element of S, and A compose B is also an element of S. Will be phi of A. Phi is in S means phi is in T. So phi A is in T. So phi A, and it will break to phi and phi B, and it will break in such a way that it respects this operation. So it will respect this operation. So naught will be turned to change to hash on there, and other structures are the same. So you see, here is A compose B is phi A compose star phi B. So structures are same. So this is a group homomorphism. So another property what we studied in group homomorphism is that phi of, let's ES, so S is S comma S naught is a group, so it has identity in S naught. Similarly, ET is the identity in T star, right? S naught and T star. So what do you show that phi of ES equal to phi of S not phi of ES, phi of ES equal to ET. How will show it? We can show it easily. Suppose, so since ES is identity, A is compose ES equal to A, right? A has the identity element ES. So for any element A belongs to S, A compose ES, we'll keep it intact. So A compose ES equal to A. So now we take we compose phi both sides, so it will result the same because phi is well defined. So phi A equal to phi this of this equal to phi of A compose ES equal to phi A, right? So phi of A compose ES equal to phi A, right? Now since not is a homomorphism, so this will break into this will turn to star, and the rest of the structure will be the same. So phi A will be phi A not ES will be phi A star phi ES, like this, right? So phi A star phi ES equal to phi A. Now you see, phi A is an element of T, phi ES is an element of T, and phi A is also an element of T. So we are now at T, and phi A is an element of T, so phi A has an inverse in T. So we let multiply phi A inverse both sides, right? What we'll get? We'll get something interesting. Let's see what you get. This phi A inverse, right? Phi A, this is star phi A. So you see, since star is a group, so star is associative. So this bracket goes to this bracket. So phi A inverse, not phi star phi A inverse star phi A star phi S. So bracket is immaterial. So this is phi. Let's say phi A is an element of T, and phi A inverse is also an element of T. So an element with the composite with the inverse will get the identity element of the group. So both are in T. So this is identity element means the identity element of the T. So this is ET, right? Now this is also ET. Now ET star phi ES equal to ET. Now you can see ET is an element of again identity element of T. So ET compose phi ET star phi ES equal to phi S. So phi S equal to phi T, right? So what do you have? In the last page we saw that R plus to R plus is a group homomorphism, and R naught to R naught is a group homomorphism. So R plus, what do you have? R plus has identity 0 identity, and R naught has identity 1, right? So sigma under, so in this group homomorphism, this sigma, this is also an identity 0, this is also an identity 0. So sigma 0 will goes to 0. Sigma will, sorry, and wait, yes. So, sigma of identity element of this group will be the identity element of this group. So sigma of 0 equal to 0. Sigma of ES equal to ET. ES and ET are both 0, right? Similarly, sigma of 1 equal to 1. Right?
Yes.
Now, okay. What you'll need? Let's see again. We have seen the homomorphism, we've seen the automorphism, and now we have to prove that any automorphism of R fixes Q, right? So we get sigma 1 equal to 1. So we utilize this fact to prove that sigma fixes Q. Now sigma 1 equal to 1 implies sigma 1 plus 1 equal to sigma 1 plus sigma 1, because sigma plus is a group homomorphism. So sigma 2 equal to sigma 1 plus sigma 1 equal to 2 sigma 1. Sigma 1 is 1, so 2 into 1 equal to 1, 2. Similarly for sigma 1 plus 1 plus up to 1 n terms. What is that? Sigma 1 plus up to sigma 1. This is also at n terms. So to get sigma n equal to n sigma 1. So equal to n sigma 1 is 1. So n into 1 plus sigma n equal to n. Similarly, so sigma fixes the natural numbers, right? Here's n is positive, so sigma fixes the natural numbers. Now we'll put the sigma fixes the integers also. Suppose for that part we use the fact that sigma 0 equals 0, right? What we prove? What we use? Sigma 0 equals 0. So sigma n minus n equal to 0 implies sigma n plus sigma minus n equal to 0, right? So this minus n, sigma minus n means plus or minus n. You can prove this. So sigma minus n will be sigma n is an element of R. So we compose with minus sigma n both sides, right? Minus sigma n plus sigma n plus sigma minus n equal to minus sigma n plus 0. So to let sigma minus n equal to minus sigma n. Minus sigma n plus sigma n goes to 0, and sigma minus n will remain, and it will be minus sigma n, right? So minus sigma n equal to sigma n. So what we have proved? We have proved that minus sigma n equal to n. So and sigma n equal to n is positive. So sigma minus sigma n equal to minus n. So what we have proved? Sigma fixes z. Now we'll use this. We'll prove that sigma fixes q. Sigma fixes q. So suppose p by q is a rational number, right? So p by q is a rational number. So what is sigma p of q? Sigma p of q, p by q will be sigma 1 by q, 1 by q plus 1 by q plus up to 1 by q times p times. P may be positive or negative, doesn't matter, right? So it will break to sigma 1 by q plus sigma 1 by q plus up to sigma 1 by q, right? How many sigma 1 by q? P times, right? So p into this will be p times. So p into sigma 1 by q, right? And now sigma 1 by q will be, we'll prove that sigma 1 by q will be 1 by q into sigma 1. How will we prove it? We'll prove it by, say, let's say, we prove by, well, we multiply by q and 1 by q into q into 1, so it doesn't matter. So it will remain like this. So it will be p by q into sigma 1 by q. So sigma 1 by q plus sigma. Okay, so q is negative. We take q outside it and q outside it, and it add it minus q times. So will be like sigma 1 by q. It doesn't matter, you can check it. So this is q times sigma 1 by q. So q into sigma 1 by q. Sorry, what I have done. Sorry. Sigma, this is a homomorphism, sigma homomorphism. So sigma will catch it all 1 by q in one bracket, single bracket, right? This is another again q times 1 by q times. So what do you get? p by q. This is q times, so q times, so q sigma q into 1 by q, so p by q into sigma 1. Sigma 1 we have proved, sigma 1 is 1. So what do you get? Sigma p by q equal to q. So sigma fixes q. Now the interesting part. Now we'll prove that sigma is if sigma is automorphism, sigma fixes R. Sigma fixes R. That is what it remains to show that sigma fixes R minus q. Sigma fixes the irrational numbers. Irrational. Sigma fixes also the irrationals. This is the most interesting part of this theorem. So let's go. Suppose let's choose an irrational in number in R. So let t belongs to R minus q. So t is an irrational number, right? So we use, let's see. Okay, another thing we missed. Before this, we have proved the sigma fixes q. So another thing we'll use is that sigma that q is dense. Another theorem is that q is dense in R. Okay, q is dense in R means means q dash means derived set of q is R, right? So t is an element of R minus q. T is an element of R minus q. So this is an element of R. So t belongs to R. So t is also a limit point of q. So this is a derived set, means that t is a derived set, means set of all limit points. Set of all limit points of q is R, right? This is called a derived set. So t is a rational number. So every point in R is a limit point of q. So t is a point in R. So t is a limit point of q. Sorry, yeah, it's limit point of q. Yes. Now t is a limit point of q. So let's again see. We'll prove t is dense in R. Now we'll prove that use this fact that a monotone increasing sequence which is bounded above converges to supremum or LVP, right? T is a limit point, right? So for now consider, so t is a element belongs to R. Yeah, so let's say t is here, right? Here is 0, here is t. You can take t here also, doesn't matter. So now we consider the set minus infinity comma t, right, intersection q. This set means this whole set intersection q. We take all the rational numbers intersection this whole set, right? This whole set minus infinity to infinity, right? This set, suppose this set is S. So suppose this is S1. So now we can easily prove that t is the supremum of S1, right? So since because you can see t is no number in this set is greater than t, so t is an upper bound, and you can see t is supremum because you can take no other number less than t can be a upper bound of S1, because if you take a number say t minus half less than in this set S1, sorry, not S1, in t minus half in this R, so we will get a rational number greater than, so suppose this is t minus half, we get a rational number in this set, since q is dense in R, it is rational number in this, it's such that t minus half is less than the rational number is such as t star, so t minus half less than t star less than t, so t star will be another upper bound, so t minus half cannot be upper bound. So similar way you can prove that no number less than t can be a upper bound of this set. So t is a least upper bound or supremum, least upper bound of S1, right? Okay, fine. Now since t is the least upper bound of S1, what will have again let's see, let's draw a picture. This is t, this is 0, say we considering the set. This is Q, right? So since T is the least upper bound of this set, so say T minus 1, T minus 1 is less than T, right? T minus 1 less than T. So since T is the least upper bound of this set, no, T minus 1 is not an upper bound. So there exists an element, say what we will say that R1. There is R1 belongs to Q, not belongs to S1. S1 means Q1 intersection minus infinity comma T, such that T minus 1 less than R1 less than T, right? And R1 cannot be equal to T because T is irrational number and R1 is rational number, so R1 is strictly less than, right? Similarly, there is this. So for now, for T minus half, there will be another rational number R2. R2 belongs to S1, right? Similarly, we will have such that there is this Rn belongs to S1 such that T minus 1 n by n less than Rn less than T, right? Okay. Now let's go back to our previous page. What would I have? Not good. It is written there. Okay. Another thing we missed is that we will now use the sandwich theorem. Okay, we will now use the sandwich theorem. That's a squeeze theorem. Sandwich theorem. We use the sandwich theorem. Now, right? Now the sandwich comes. Rn. Now get a sequence Rn belongs to Sn such that this sequence T minus 1 by n less than Rn less than T for all n greater to 1, right? Now we use the sandwich theorem. So what sandwich theorem says? Sandwich theorem says is if an less than bn less than cn, then limit limit an equal to a and limit an equal to a and limit bn equal to a n tends to infinity, then limit cn equal to a, then limit bn equal to a, right? Now we take the limit in this case, in this inequality. So limit n tends to infinity T minus 1 by n. So I have not mentioned the steps in the sandwich theorem. I'll try to mention it here because some of you may not have read sandwich theorem, so I'll mention it. So what the step is, another step which includes in the sandwich theorem is that if an less or equal to bn, this sequence is this sequence, the limit of this sequence will be the limit of n will be less or equal to limit of this. Limit will be if limit turns less than to less or equal to, and similarly limit turns this less than to less or equal to, right? We will prove this. We will prove this inequality shortly. We will result shortly. Now by sandwich theorem, this not by sandwich theorem, by taking the limit, it is independent of n. So this is t. This is null sequence. This goes to 0. So this is t minus 0 is equal to Rn. This is limit n tends to infinity. Similarly, limit n tends to infinity. Rn is equal to this is also independent of Rn. This is independent of n. So it is equal to t. So what left hand side goes to t. Is equal to limit Rn. This is equal to t. So what do you have? Limit Rn equal to t. So well, now I explain the step in the sandwich theorem. That is an less than bn for all n belongs to n implies limit an less or equal to limit bn, right? Now we'll prove it. We'll prove. So to prove this, we'll prove that un is a sequence which is a minus bn less than 0. Now for all n belongs to n, then limit un is less or equal to 0. So On the contrary, so to prove this claim, suppose limit un. So what we have, un is a sequence which is less or equal to 0, or is 0, or is positive, is negative, this is negative. So un is less than 0, so limit un is less or equal to 0. So limit un, so suppose limit un greater than 0. So this is limit un greater than 0, so un is positive here. So there exists as some epsilon such that u minus epsilon is still greater than 0, right? So limit un. So limit un is say u. So there exists epsilon greater than 0 such that u minus epsilon greater than 0, right? Now we use that for, so we have gotten epsilon. So for each epsilon, since limit is u, so limit is un equal to u, so for each epsilon greater than 0, there is m belongs to n, such that this happens. What happens? That a minus epsilon less, what is the sequence? un less than e plus epsilon for all n greater or equal to m. This is the definition of the limit of a sequence, right? So now we have u minus epsilon greater than 0, right? So u minus epsilon greater than 0, here 0 less than u minus epsilon greater than 0 means 0 less than u minus epsilon, right? So you use this inequality here, so you get this. Now what do you get? un, now we un greater than 0, we composing these two inequalities, we get un greater than 0, or 0 less than un, or un greater than 0 for all n greater than m, which contradicts the fact that, in fact, that un is less than 0 for all n. This fact, it contradicts this fact that un less than 0 for all n, but we get un greater than 0 for all n. So it's a contradiction. So we hence the claim is proved that limit un that what's the claim? That limit un is less or equal to 0, right? So limit an minus bn is less or equal to 0. So limit n minus bn is less or equal to 0. So limit an is equal to limit bn. Similarly, so if this results here, so this, right? So what do we have now? We have that limit r is equal to t. So similarly, we use another theorem which states a monotone decreasing sequence which is bounded below, converges to its greatest lower bound or infimum, right? So let's see again, go through the pages, turn over the pages. What do we have? Now here we consider the set s minus infinity t intersection q. Now we'll do the inverse. So we have t belongs to r minus q, right? So r minus q minus into r. So now we'll consider the set t comma infinity, right? We'll consider the set t comma infinity intersection q. This set, similarly, as in the previous part, we can prove that t is the infimum of the set. This set is say S2. T is the infimum or GLB, greatest lower bound of S2. So since similarly t is greatest lower bound of S2, so similarly we get another inequality like this. The inequality will follow like this. I'll write in short. T less than t plus 1, we get a member of Sn, S1 belongs to S2, such that this happens, right? For this is epsilon equal to 1. We take epsilon equal to 1, we get an element of this S2. S2 is what? T comma infinity, decision q. We get an element. This is t minus 1. This is t minus half. This is similarly, right? Sorry, not t minus 1. This is t plus 1. This is t plus half. So for t plus 1 half less than greater than this is 2. So for similarly for t plus 1 by n, we get Sn, right? Similarly, we get what we get is limit t is equal to limit Sn is equal to limit t plus 1 by n. So by sandwich we will get limit Sn is equal to t is equal to t. So limit, oh, so in the previous part we get Rn, now we get Sn, right? So limit Sn tends to infinity Sn equal to t. So viewers, what you have seen? What you have seen that Sn, you can see Sn. Okay, Sn. Okay. Okay. What you have seen that Sn is greater than t always, and Sn converges to t. Sn converges to t. Right? And in the previous part, what you've seen that Rn is less than t and Rn converges to t. Right? Rn is less than t and Rn converges to t. Rn is less than t and Rn converges to t. Right? So in the composite inequalities, what we have got is that in between t we have got Rn and here we have got Sn, right? And Rn is less than t and Sn is less than t. Now is this part, that q, that sigma. The sigma fixes q, right? We have proved this. Sigma fixes q. If you can prove that sigma Rn less than sigma t less than sigma Sn, we are almost done, right? Because sigma Rn is sigma fixes q, so sigma Rn will be Rn, sigma Sn will be Sn. Rn converges to t, Sn converges to t. By sandwich chain we get sigma t will be, and sigma Rn is okay. Sigma Rn is what? Yes, sigma Rn is Rn converges to t. So sigma Rn. Wait. Well, well, friends, now even if we prove that, well, to apply sigma, what will have to prove that sigma respects. Okay, Rn. Okay, well, now the critical part of the quest theorem. So Rn converges to t, Sn converges to t. So well, and sigma Rn is another sequence of sigma Rn equal to Rn converges to t, sigma Sn equal to Sn converges to t, right? So what we want to do is now that we have to take sigma both sides, right? To take sigma both sides, we have to prove that sigma respects the inequalities, right? What I have shown here, what I wrote here, sigma respects inequalities, right? Now we prove that sigma respects inequalities. So friends, if you prove sigma respects inequalities, we're done, right? Well. Because it will be sigma t, is sigma Rn equal to t and sigma Sn equal to t, so sigma t equal to t. Right? Yes, we're done. Right, well, yes, we're done. So the only part we left is sigma respects the inequalities. Only thing we to prove this part, we only thing we need to prove that if x greater than 0, then sigma is greater than 0, and the rest of the part will follow. This part will follow from this. Sigma b will follow from the homomorphism part, right? We can show that if sigma, so x greater than 0, so x is positive, so we can x is positive, so x can return as x to y square, because where y belongs to r, right? So sigma x equal to sigma y square, sigma x equal to sigma y square, so sigma x equal to sigma y dot sigma respects the homomorphism, sigma is a homomorphism with this dot, so sigma y dot sigma y equal to sigma y square, right? So sigma y is a real number, sigma is a map from R to R, so sigma y is a real number, so sigma y square is a square of a real number, so it's greater than 0, so sigma is greater than 0. only thing we left to the rest part will follow from easily, because if x greater than 0 implies sigma x greater than 0, right? So now if say, what to say u minus b, so say u minus u greater than b, right, implies u minus b greater than 0, right? By sigma, by this part, sigma u minus b, sigma is a homomorphism with the plus, so sigma u minus minus sigma v greater than 0, right? So sigma u greater than sigma v, so sigma respects the inequalities, right? We are done. So since sigma respects inequalities, we use this part to this part. Sigma respects inequalities, so using it in star, we get star. We have is earlier, no, okay, this is the first star. Okay, so we get, what we get is sigma Rn less than sigma t, this star, sigma Rn less than sigma t less than sigma Sn, and sigma Sn. Now we use sandwich theorem, limit sigma Rn, so we get this should be this equal to sigma t, limit sigma t is equal to limit sigma Sn. What you have proved, sigma Rn goes to sigma Rn equal to R, sigma fixes Q, so Rn is a member of Q, so sigma Rn will be R, so sigma Rn will be Rn, so sigma Rn will be Rn, and Rn converges to T. You set Rn converges to this, you know, right? Sigma Rn is equal to sigma T. This is independent of n, so this remains as sigma T, and this is sigma Sn. Sigma Sn is Sn, and Sn converges to T. We write in the next percent sigma Sn, sigma fixes Q, so sigma Sn equal to Sn. Q and Rn and Sn belongs to members of Q, so sigma Rn, so and Rn limit, you have seen that limit Rn tends to T. Here we seen limit, and limit Sn tends to T. So we have sigma T is equal to sigma T is equal to T. So we are done. Sigma T equal to T. What we have taken? We have taken that sigma. We have taken that sigma T is a member of R minus Q. We have already proved that T fixes Q, and we have taken an arbitrary element of R minus Q. That is, we have taken arbitrary irrational numbers, and we have proved that sigma fixes that element too. Implies sigma fixes Q union R minus Q. That is, sigma fixes R. Sorry, I may get the wrong notation. Sigma fixes Q means sigma Q equal to Q, maybe, probably, but what it means is that sigma x equal to x. Sigma fixes Q by that means sigma x equal to x, right? So sigma x equal to x for all x belongs to R. So sigma equal to identity. What are the only identity? Only one identity is there, right? So only automorphism of R is the identity. So we are done, right? If you like, please like, comment and share. Okay, bye.